Okay, algebra students, we're going to talk about 7.6 today. That's chapter 7, lesson 6. These are rate problems. Now, rate problems are still systems of equations. They're just word problems. So there are real life type examples of how a systems of equation works. So a few things that I want you to remember is that systems of equations means that you actually have two lines. Okay, and they are doing, some equation can represent the rate of travel of something, a helicopter, a boat, a person, whatever it is. That would be, your first line. Your second line represents the rate of travel or the distance traveled, some sort of an equation that's for a second item or a second person. And where they intersect is where they would meet. Okay, sometimes if you're talking about like helicopters or planes, you might say, where's the point at which one crosses the other or one overtakes the other? So you have to find this point of intersection, which we learned 3 ways to do last week. And then you can say, beyond this point is where helicopter A is traveling slower than B, or helicopter B has overtaken helicopter A. So thinking about the fact that these systems of equations are these two lines and that we do know how to find their point of intersection. And remember, you can always use any of your methods. So this is the lesson where you get to choose the method that you like the best. Or if one method is not working for you, you can always fall back on another method. So let's remind ourselves that we can graph to figure out that point of intersection. We can eliminate a variable. Whoops, I spelt it wrong. Eliminate. So we can use elimination and get rid of either the x or the y in order to solve for the opposite one. We can also use substitution. So I don't care what method you use the one that works best for you. You have the other options to fall back on if something's going wrong. Okay, but remember what it means to be systems. It means that you have those two equations of a line and you're looking for that point of intersection for them. Now with the word problems, the other thing that's really important is that you be able to tell me what x is and what y is. And that's going to be very key from the very, very beginning. If you're talking about two helicopters, X is the blue helicopter, Y is the red helicopter. If you're talking about nuts, X is peanuts, Y is almonds. And you need to be able to name them right away before you ever start working on your equations as to what your X stands for and what your Y stands for. And you want to make sure that you put that on your paper. So let's take a look at our next page. Oops, I didn't go too far. So this is a picture from your book, and it says, recall that the formula for distance traveled is distance equals rate times time, or D equals RT. So I'm going to write it down here. D equals RT. This is something that we learned many, many years ago. D is your distance, R is your rate, and for all of these problems, we're going to say that our rate is constant, which means that we have linear equations. Okay, and T is your time. The object moving at a constant rate is said to be in uniform motion. Throughout this lesson, assume that the people or the objects are in uniform motion. That means that your rate is constant, it's not changing, and you are dealing with linear equations, which means that you have straight lines that continue on and on forever and ever. Now, it also reminds you that when you're reading these rate problems that you want to look for those pieces of information and the relationships between them. So they gave you an example. A rate relationship is where the object is moving twice as fast as a different object. So if you're saying something is twice as fast, you can always figure it out in your head a little bit. Like if object A is twice as fast as B and B moves at 1 inch a minute, then A is going to move at 2 inches a minute. If object B moves at 4 inches a minute, then object A is going to move at 8 inches a minute, which is 2 times B. So you could essentially say that A is really 2 times B. So whatever B is, A is 2 times that. And therefore, you have something that you can substitute in. So kind of remember that when you're playing with the words in these problems. Time relationship is when they give you a total time. They'll say this happens in so many minutes. The total time of this was so much. And a distance relationship is where A is catching up to B. Whether that's a helicopter or a person, a boat, a swimmer, it doesn't matter. One thing, they're relating it to how far it travels and it's going to pass another object. And you can see that in the linear equation, that if I just draw this next line, line B, it passed line A at that point, okay, or it caught up to line B at that point. Now, the reason that they say this to you is because remember that in algebra, you can set any of these equations equal to each other. So if I want to solve for rate, I can say it's time divided by distance. And if I want to solve for time, I can say it's distance divided by rate. And that's just isolating your variable. But they're all exactly the same thing. You're using the same formula, just in different manners. And this is going to be the formula that you're going to pay close attention to for this particular lesson. All of your equations are utilizing one form of this distance formula. All right, let's move on. Let's take a look at our first problem. So our first problem says, we're talking about aircrafts. A helicopter leaves an airport and flies north at 180 miles per hour. An hour later, an airplane leaves the airport flying in the same direction at 330 miles per hour. Write a system of equations that can be used to determine how long it will take the airplane to overtake the helicopter. Okay, so the first thing that I do is I almost always try to draw myself a little picture. And so I might say, okay, here's my airport. And the helicopter leaves the airport and flies north. Okay, so I'm going to move my airport. I'm going to put my airport down at the bottom. My airport is down here, and my helicopter leaves and he flies north, okay, at 180 miles per hour. And then it says an hour later, the airplane leaves the airport flying in the same direction, and it flies at 330 miles per hour. It wants a systems of equations that can be used to determine how long it will take the airplane to overtake the helicopter. So they are essentially flying in parallel lines, but overtake means at what point will this airplane guy pass the helicopter and be beyond. So what is this point? Okay. Now we have to remind ourselves that we want to start with, what do our variables mean? So I'm going to say that my x is my helicopter. And I'm going to change the color to keep it consistent with the drawing that I just did. So my x is my helicopter. And my y is going to be my airplane. Now I have to come up with a systems of equations that represents this, which means I need two different equations. And since we're actually trying to talk about when will it overtake the helicopter, and we're looking at this line here that we've kind of dotted and drawn, when will it pass, we're actually talking about time. So at what time will that airplane pass the helicopter? So what I want to look at is x being the helicopter's time and y being the airplane's time. And now let's see if we can make some equations. So we could say something like the airplane is equal to the helicopter, which is x, minus 1 hour. And why is it minus 1 hour? Well, it's really minus 1 hour because that airplane flew. He took off an hour after. It says an hour later the airplane left, which means that this helicopter was flying for an hour more than the airplane was. So the airplane is the helicopter's time minus 1 hour. And now we could talk about the other piece of information they gave us, these rates of speed. And since we know that they're going to be, they're traveling at a constant rate, one is traveling at 180 miles an hour and one is traveling at 330 miles an hour, we can set them equal to each other. We can say that we have the airplane times his rate of speed, which is 330, is equal to the helicopter times his rate of speed, which is 180. And we just made two systems of equations, or we made two equations, which makes a system of equation. So we have two equations, and now this problem doesn't actually tell us that we want to solve it. But because we want to go ahead and practice it, because all of our homework is going to be to solve it, I want you to try to substitute it in. This one is a great method for substituting because one is set equal to y. And so I can take this value and I can plug it in here and I can solve for x, which is the helicopter's time. And once I know the helicopter's time, I can figure out the airplane's time. Okay, so I was worried I didn't have enough space. So here's a new page, same formulas that we just came up with, but let's go ahead and try to solve it. So I'm going to use that substitution method, only because I see that this guy can substitute in for the y value here really easily. So I'm going to say that I have 330 times the quantity x minus 1 is equal to 180x. And from there, I need to distribute my 330. So I get 330x minus 330 is equal to 180x. Now I need to get my variables on the same side of the equation. So I'm going to subtract 180x from both sides. And I end up with 150x minus 330 is equal to 0. Now I want to move that 330 to the other side, so I'm basically adding 330 to both sides, and I end up with 150x is equal to 330, and to get my x alone, I need to divide by 150, so I end up with x equals 330 divided by 150, which is 2.2. And remember, we were talking that x is helicopter's time, so this must be hours. So this is a little bit more than 2 hours. And if we really want to know how many minutes this would be, it would be 2 minutes out of 60. Okay, and that would give us an exact minutes. So we'll just leave it with 2.2 hours. But that's the helicopter's time. So we need the airplane's time, so we would take the equation y equals x minus 1 and plug back in our x. So y is equal to that 2.2 minus 1, which leaves y as 1.1 hours, which really makes sense because our original problem said that the helicopter left before the airplane. So the airplane was flying less time. So the airplane traveled for 1.1 hours and the helicopter traveled for 2.2 hours. Okay, so what I'm going to do from here is I'm going to put up another problem that's very, very similar, and I want you to pause the video and try to solve it together and see what you get. And then I want you to play the video and check it. So let's look at the next problem. The next problem says, what if the airplane leaves a half hour after the helicopter? Write a system of equations that can be used to describe how long it will take the airplane to overtake the helicopter. So it's a little bit different in that the airplane leaves only a half hour after the helicopter. So I want you to pause it. I want you to come up with the two equations that you're going to use. I want you to attempt to solve them and see if you all get the same answers. So I'm assuming you've paused and taken a chance to solve it. So the equations that you should have come up with would be that your first equation would be, if you were dealing with y still being the airplane's time and x still being the helicopter's time. And again, it's really important that you write down for each of your problem what your x and your y stands for. So if these are your two variables still, then you would have come up with the equations y is equal to x minus 0.5, or you could have said y equals x minus a half. Okay? And then your next equation would have been 330y is equal to 180x. And since these are your two equations, which is all that this problem actually asked for, but then I told you solve for it. So if you had solved, you would have ended up with x was equal to 1.1 hours, which means that your helicopter flew for 1.1 hour, and that would leave your airplane as 0.1 hour of flying time. Okay? All right, let's try a different problem. It's a little bit more complicated. It uses a different set of the relationships. So we have a kayak, and during a kayaking trip, a kayaker travels upstream against the current, okay, and downstream with the current at the speeds shown below. The speed of the current remains constant. Find the speed of the kayak in still water and the speed of the current. Okay, so x and y are what they want you to solve for, and the x is going to be the speed of the kayak in the still water, whereas the y then has to be the speed of the current. Okay, now think about, I kind of got to think about what this means. If you're going upstream and you're going against the current, that means the current is running the other way. So look at this first kayaker. He's headed in this direction, but the direction of the current is going this way. That means it's going to be harder for him to travel upstream, which is why his rate is 4 miles per hour. However, downstream, when he's traveling in the same direction as that current, he can travel faster, 6 miles per hour, because the current is pushing him along and allowing him to go a little bit faster. So let's give our variables some names. Okay, so let's utilize the x and the y, and let's say that we're going to call our x the kayak in still water. Okay, and so it's a speed, which it means that we're looking at rate, right? And the y is going to be the speed of that current. And these are the two components that I underlined originally because I could tell that that's what they wanted me to solve for. It says find. And therefore, I have to give them my x and my y values. These are the two things I have to find and I have to solve for. So the first thing to do is to try to come up with an equation that relates these pieces to each other. Okay? Well, we know that this kayaker moving with the current in the same direction goes 6 miles an hour. So that means my kayaker, or the speed of my kayak in the water, which is x, plus that current, which is y, gave me the rate of 6 miles per hour. Okay, that's how fast it was going. But these guys up here going upstream, it went in opposite directions, which means that it's taking away the travel time. It's hurting the guy. So it only traveled 4 miles an hour. But what was happening? We have the speed of the kayak again, which is that x, but it's against the current. So it's minus that current gave me 4 miles per hour. And now I have two equations. And you have 3 ways that you can solve these equations. So these are the equations that we're going to use. Let me turn to a new page. Okay, so I have my 2 equations that we just came up with. The x plus y equals 6 and the x minus y equals 4, and then I just reminded myself of what my x and my y meant. The x was the speed of the kayak in still water, the y is the speed of the current. So now we can use any method we want, but right away I see that if I add these guys together, my y's cancel out. So I'm actually using elimination. I'm eliminating the y's. So I'm going to add the two equations together, and I end up with 2x equals 10, and when I isolate my variable, x is equal to 5. Well, what does 5 mean? It's really 5 miles per hour, because remember, my x is talking about the speed, and speed is in miles per hour. So this 5 miles per hour is the speed of the still water, or the kayak in the still water. Okay, it means without a current, just the kayak in that water by itself. So now that I have x, I can plug it in for one of the equations, and I can now solve for the speed of the current. So I can take any equation I want. I'm going to do x plus y equals 6, and I'm going to take this 5 and I'm going to plug it in. So I get 5 plus y equals 6. So basically I'm adding a negative 5 to both sides. Whoops. And I get y is equal to 1, which is 1 mile per hour, because again, we're talking about the speed of the current. So 1 mile per hour is the speed of the current. Okay, and it's really important that you, write out these word problems and what they mean. This piece up here where I keep telling myself what x and y are is extremely important. And then, of course, my answers have to be in this word problem format where you're related back to the problem and tell me what you've actually solved for. Okay, I do have another problem for you to try on your own. So let's take a look at it. The problem says the kayaker travels upstream at a speed of 2 miles per hour and downstream at a speed of 5 miles per hour. The speed of the current remains constant throughout the trip. Find the speed of the kayak in still water and the speed of the current. So I want you to pause the video. I want you to work on finding your two equations and solving them, and pause the video now. So I'm assuming that you have paused and you guys have worked together. So our equations are essentially the same as they were the last time, where we had x being that speed of the kayak in still water. And if you reversed them, it's not that big of a deal as long as you stay constant and as long as you tell me what it is that you used for your x and y. And so y is then the speed of the current. And so my two equations would be x, so that speed of the kayak going downstream with the current, that would be adding it. Adding the current, y, is 5 miles per hour, which means that going upstream, that kayak's speed has to take away from the speed of the current, and it only went 2 miles per hour. So now when you solve them, what you get is that x is 3.5 miles per hour, and y is 1.5 miles per hour. So my current is 1.5, and my speed of the kayak on its own is 3.5. And these become my answers. Okay, so what you're going to do next. Okay, algebra, this is your homework. Page 415 to 417, and I'm not going to give you a whole lot because I do realize these guys are hard, but you need to do numbers 3 through 13 odd, and these guys are super easy. These are the D equals RT problems, and the answers are in the back of the book, so make sure you check yourself. Then problems 17 through 24 all. These are the hard guys. And I think I put on the subplans through 23, but I really want you to do number 24. It's a two-part problem, and I do want you to attempt it. And then do 27 through 29. All, that's only 3 of them. These are the spiral reviews and they're multiple choice. Just show me your steps in your work, but they shouldn't be a big deal. These guys are probably the challenge guys. All right, I will see you guys tomorrow.